Okay, I'm just going to call on people because I'm hoping this goes really quickly. These are things that we've got memorized and have them down pretty cold. Let's see, Colson, how about 8 squared?
64.
Can you tell us why?
Because it's 8 times 8.
Yeah, because it's 2 8s, right? Let's see, we did this one already, Cy.
27.
27, because it's 3 3s, right? 5 cubed, one we ought to have memorized. There's a certain number of perfect squares and perfect cubes we ought to have memorized. Angela, right? Close. 5 quarters, 525. So it's going to 525. So it's going to be 125. Okay. 5 times 5 is 25. Times another 5, 125. And then the last one, if you've got this one memorized, great. Most teachers only make you memorize to 12 squared. If you've got memorized up to 20 squared, that's really helpful. This one is, Dane?
196.
It is 196. Now, if you need a calculator for any of those, that's totally okay. Yeah.
Screen is still frozen.
It is. Thank you very much. Okay. I will forget that every once in a while, so I apologize. Okay. All right, so we got 64, 27, 125, and 196. So a whole bunch of the stuff that we do in math learns how to do something. It means we learn how to do something, and then we learn how to undo it. Okay, when two operations undo each other, the fancy word for that is we call them what type of operations? What is it? Who said that?
Me.
Very good. Nice job. We call those inverse operations. Okay, you're going to get really familiar with lots more inverse operations over the next couple of years. So a radical, or in other words, a root, is one of the tools that we undo exponents with. There's another one that you're going to learn hopefully later this year. And there are 3 parts of a radical expression. They are the radical sign, the radicand, weird word, and then the index. So the index is this little number right here that's in kind of the crook there. So this is the index. That symbol, no matter what number is in there, is called a radical sign. So we're just going to call that a radical. And then the stuff that's underneath there, no matter how easy or how complicated it is, we call that the radicand. All right? If there's no index, so if it looks like this and there's no number there, it's not a 1, it's a 2. So if there's a 2 there, then we mean it's a square root. If there's a 3 there, then we need to find the cube root. If there's a 4 there, we need to find the 4th root, 5, 5th root, 6th, 7th root, and so forth. Okay? So this would be the 5th root. So I'm going to slide down here. Now you've talked hopefully a lot about square roots and cube roots, maybe not so much about the other ones, but the ideas are basically the same. So we're going to run through some properties of radicals. So here's the property, and then here's an example. So if we have the nth root, and I know that sounds weird, of a to the n. So if we take a base and raise it to the n, and then we find the nth root. In other words, if the index matches the exponent, they undo each other and we just end up with an a. There's this cool property if you've got a multiplication problem as the radicand, you can do the radical of the first part, the radical of the second part, and then we can multiply them together. And if there's 3 factors in there, 4 factors, you can find them all separately. And then this one's awesome because if you've got a fraction underneath the radical, you can find the, oops, I forgot something. And people do this all the time. There should be an n left in that crook, okay? So this is going to be an nth root of a on top and an nth root of b on the bottom. Now, before I do any examples and run over here and take a look at this, and then we start doing problems, I want you to note this. So there's stars by it. Would you put your own stars by this? Most people forget. They're always thinking, oh, the rule only works this way. But there are lots of things in higher math that if you remember some of these general properties and theorems and things like that, they actually work in both directions. So if you saw something like this and wanted to put it underneath the same one, that would be okay. If you saw an nth root on the top and an nth root on the bottom and wanted to write it as one single one because it's simplified better that way, totally okay to use those in both directions. So if this is the square root of a squared, you just end up with a. If this is the cube root of ab, you can write it as the cube root of a times the cube root of b. And again, don't forget the index. I'll do that sometimes. It'll be a cube root or a 6th root or something, and I'll just leave it off. So you got to have that. That's really important. And this would be the 4th root of a over the 4th root of b if we applied that quotient property there. So little box here to remind us how square roots and cube roots work, and then it kind of works for the other ones. So square roots change groups of two factors, in other words, pairs, under the radical into one factor on the outside of the radical. So that's kind of how they undo squaring. Squaring takes one factor, turns it into two. Square root take two factors and turns it into one on the outside. So cube roots, they change groups of three factors, or in other words, we'll call them triples. So if you've got a group of three of the same factor underneath the radical, you can make it into one factor on the outside of the radical. So square root, we're looking for pairs. Cube root, we're looking for triples. Fourth root, we're looking for groups of four. Fifth root, we're looking for groups of five, and so forth. Okay? Now, radicals that are simplified have no fractions underneath the radical, so you can't leave a fraction underneath the radical. There are no radicals in the denominator. No radicals in the denominator. Got that one right. Denominator. And this part's a little interesting. No groups of factors left inside the radical that could be represented by a factor on the outside of the radical. And we'll talk about some examples that use that. So those are some big rules there. We don't leave a fraction underneath the radical. We don't leave a radical in the bottom of a fraction. And we also make sure that we simplify completely. We pull out all the factors that we possibly can based on how many factors there are and what root we're looking for. Okay, are there any questions? All right, I'm going to make this a little bit bigger because then it makes it easier for me to write and for you to read. So we want to simplify this one right here. So the square root of 80. Now, if we were going to do this the long way, we might say, oh, I'm looking for factors. We might do some prime factorization. So I might do 80 times 10. If you do it a different way, that's fine. 2 times 4. 2 times 2. And this is 2 times 5. Now, I'm going to write it like this. This is a square root, so notice that the index matches up. I've got a 2 and another 2 and another 2 and another 2 and a 5. And I'm just going to try and put a dot in between all of those. So, square roots. I'm looking for groups of 2. I'm looking for pairs. Pair of 2's, put one on the outside. Pair of 2's, put another one on the outside. And remember, this is all multiplication, so that's a multiplication problem right there. The 5 is stuck underneath. Can somebody tell us why the 5 is stuck underneath? Why is the 5 stuck underneath? Sai.
There's not another pair.
There's not another one to pair it up with, so it's got to be stuck underneath there. Would it have been okay to leave this pair of 2's underneath there? Nope, because that's an example of a pair of factors, a number of factors that can be pulled on the outside and represented out there. So if we're going to simplify this completely, this is going to end up being 4 radical 5, and that's usually the way we say that. Now, that's about as bare bones and nitty gritty as we can get on a problem like that, but can you think of another way to do this? If you can't, that's fine. This works, doesn't it? Okay, I'm going to change colors. Watch this. What if I wrote that? What if I knew 5 goes in there 16 times? 5 times 16 is 80, isn't it? And there's that little property that says, hey, you can break it up like this. What's the square root of 5? I don't know. It's some irrational number, but what's the square root of 16? 4. 4 radical 5. Okay? Either way's fine. The cool part about math is, regardless of the different route you took to get there, the answer should be the same. Okay, any questions there? I'll take a volunteer on this one. Brittany, good to have you back. What is it? It's x. Done. If the index is the same as the exponent, that means we're looking for 2 factors on the inside, and that's exactly what we've got. So they undo each other, and there we go. How about part C? It's on here for a reason, to make you think. You want to give it a shot? Zach, right?
Yeah. Would it be, could you split it into -8 and 8?
We'd have to do -6 and 6.
-6 and 6, sorry. -6 and 6, and then you could do. Wait, no, you couldn't do that.
I love the thinking.
So if you break it down into -2 and 3, and then a 2 and a 3, and then you take out the 3's, then you'd be left with 3 square root of -2 times by 2.
Yeah, we're going to end up with a mess here. Okay, so I want to remind you of a couple things. I don't want to spend a bunch of time on this, but I want you to remember this. There are two things that cause domain issues that so far we know we can't do in math. Here's one of them. The first thing is you can't divide by 0, not allowed. The other thing that we can't do yet, we're actually going to talk about it in a couple days, is you can't do this. You can't take the square root of a negative. The reason why is, for the time being, there's no number that when you square it, it turns out to be a negative. You got a 6 and a -6, or a -6 and a 6. There's no getting around it. Even if you break it down to 2's and 3's, one of them is going to have a negative on it, and then you can't pair those up. It's not that this can't be simplified at all, but we're going to shelve this for right now, and we're going to say you can't get a real number with that. Okay? Yeah.
Couldn't you split it into 6, 6, and -1, and then have 6 square root -1?
You can. You can do 6, 6, and -1, and then you'd have a 6 on the outside and a square root of -1 on the inside, and we're going to talk about that in a couple days. Okay? Nice idea. Take a look at the next one. That's different on this one. That has a negative, but what's different about it? It's a cube root. So what are we looking for? Groups of 3. And what's interesting about negative in groups of 3? Dane? Go ahead. Tell me what are you going to say?
I'm just gonna say the answer.
What is the answer?
I think it's just 2.
You think it's just 2?
Yeah.
Okay. Positive 2 or negative 2?
Positive. Wait. Negative. Wait. I don't know.
Somebody want to help him out? Lizzie?
I think it's negative because a negative times a negative is a positive, and then a positive times a negative is a negative.
Yeah.
What are we looking for? Groups of how many with a cube root? I got to put it on here, by the way. Don't let me forget those. Cube root, we're looking for groups of 3. So the answer on this one is -2. Let me show you one more thing that might be kind of cool. Doesn't that work?
That's what
Doesn't that work? Isn't -8 -2 cubed? There are those 3 -2's represented with an exponent, and then we can just apply those as inverses of each other. Okay, take a look at this one right here. There's a 5 on the outside. Again, please note that this is a square root, so we're looking for pairs of factors. If I were doing this, I didn't do 80 on that top one for no reason. 5's on the outside. Stop and think about this. This is 16 times 3. And an x squared and a y. I'll make it just a little bit more explicit. Isn't that a 4 times a 4 times a 3 times an x squared times a y? And we're looking for pairs. I have a pair of 4's, and I have a pair of x's. So this is a 5 on the outside. That was there to begin with. That 2 4's, pair of 4's on the inside is represented by 1 4 on the outside. And I only have one x on the outside. What's stuck underneath? A 3 and the y, because there wasn't anything to pair them up with. Now, we're not going to get technical about this. This is a 20x radical 3y. I'm going to say this, but I'm not going to make you actually do this. Technically, there should be absolute value bars on the x. Technically, there should be absolute value bars on the x. I want you to think about why that should be. Okay? Take a look at this one. We're looking for groups of 3. So here's what I'm going to do. Just to show all the thinking. That's really what's going on here. Now, you don't have to do that on every single one of these. Group of 3, 2 on the outside. Group of 3, another group of 3. So what's on the outside? Luke?
2x squared y.
Okay. There is a y. Why is there a y?
Because there are 3 y's.
There's a group of 3. Okay. Don't forget to have the right index. This is a cube root, so don't forget that. So those, I've got a 2 underneath there, and I've got, what else is stuck underneath there? X. Okay. Now, Again, that's showing every ounce of work there. Okay, watch. Okay, I need you looking up here. Okay, cube root, we're looking for groups of 3. That's 4 2's. How many groups of 3? 1, with 1 left over. That's why there's 1 on the outside. Oops, I didn't put the 2. That's not very dramatic. Okay. 4 2's, group of 3, 1 on the outside, 1 stuck on the inside. If you have 7 x's, how many groups of 3? 2. So there's the 2 on the outside. How many are left on the inside? 1, because that 1 was left over. 3 y's, how many groups of 3? 1. So that's why there's 1 on the outside, none left on the inside. Everybody good with that? Okay. Would you look at that last one? It's a 4th root, so we're looking for groups of 4. Take a look at that one. Ready? Good? Okay. 32 is 5 2's. 2 to the 5th is 32. We're looking for groups of 4. So if I have 5 2's, how many groups of 4 do I have? Only 1 group. So that's going to be 1 2 on the outside. So I'm going to slap a 2 out here. I took 4 of them out. There's 1 left underneath there. So I'm going to have a 4th root. I'm going to have a 2 underneath there. I've got 5 x's. Same deal with this. If I've got 5 x's, I've got 1 group of 4. So that's going to be an x on the outside and an x left underneath. And if I have 11 y's, how many groups of 4 is that? 2. How many left over? 3. So that means we're going to have a y squared on the outside and a y cubed on the inside. Now, this looks like you ought to be able to take out a y cubed. It looks like, hey, that's a pretty big exponent. You got to be able to take something out. But the problem is we're looking for groups of 4. Any groups of 4? Not even close. This one's kind of close, but not quite there. So this is 6, x to the 3rd, y to the 3rd. Am I right about that? Check my penmanship right there. And then, 4th root of 2xy cubed. Circle that. Any questions? Okay. You have 5 problems on your assignment that are like this. Okay, and this is something new that we've added this year. This is a really important skill. It's called rationalizing the denominator. Here's the basic idea. Gotta listen. Fractions are hard enough. Things with denominators are hard enough without making them have ugly numbers in the denominator. So when we say rationalize the denominator, what we mean is make the denominator a nice number. Okay? Not something ugly that goes on forever decimal-wise or something like that. So that's what we're talking about. So here's the rule. Okay, this is not okay to have a fraction underneath the radical, so this is what we do. And this might stretch some thinking a little bit, so be ready. Square root of 5 over square root of 2. Well, great. Now there's not a fraction underneath the radical, but there is a radical in the denominator. And square root of 2 is an irrational number. If you throw it into your calculator, it goes on forever and never has a repeating pattern. That's an ugly number. So let's think about this. I want to simplify what's on the bottom. I want to make it a nice number. In order to make this a nice number, the index isn't written, but it's a 2. So we're looking for groups of how many? Groups of 2. This is a trick. Get used to it. What we're going to do is we're going to multiply by a funny looking 1. Does everybody agree if I write down the same thing on the top as I write on the bottom, I'm multiplying by 1? Same thing over same thing is 1, right? Yeah. School bus divided by a school bus is still 1. I just made the problem look more complicated. I multiplied by a funny looking 1, but here's what it does for me. And remember those rules that we said you could use backwards? This, all I'm going to do is I'm just going to multiply those together. A 5 and a 2, there are no pairs, so I'm going to write this as radical 10. But look at the bottom. I'm going to put them underneath the same radical. I'm not even going to bother to simplify it because I know what are square roots looking for? The index is 2, so they're looking for pairs. Have we now made it so there's a pair of 2's in the bottom? Yep, now we've made it something that we can simplify. So here's the answer. Radical 10 divided by 2. Now, don't do this right now. You can do this on your own time. If you go home or later today, put radical 5/2 in your calculator, it will give you an ugly decimal. If you put radical 10 over 2 into your calculator, it will give you the exact same ugly decimal. Okay? Which one looks nicer? The one with the 2 on the bottom. Okay, that's why we do this. Everybody ready? Okay, I'm going to change colors. Take a look at this one. The 4 looks really nice, but radical 5 is awful in the denominator. So we're going to rationalize the denominator. It's a square root. How many more 5's do I need? I only need 1 more, so I'm going to multiply the top and bottom by radical 5. So on the top, I have 4 radical 5. How many 5's do I now have underneath the radical on the bottom? 2. And if I've got a pair of them, I can take them out. So what comes on the outside? A 5. Circle that and we're done with that one. Any questions? We good? Okay. Next one. These are plain old numbers. You can deal with them just like plain old numbers. That's the fraction 5 over 15. So that is the fraction 1 on the top and 3 on the bottom. Now, I might make a fraction bar a little too long sometimes, so I'm going to say, hey, you know what I can do here? I can use that rule backwards. I'd rather put them underneath the same radical. In which case I have 1 over 3, and I have radical 1/7. So this would be 1/3, radical 1 over radical 7. Now, what is radical 1? What's the square root of 1? Oh, come on. 1. Okay. So does everybody agree that this is what we've got so far? I'm not done. We okay with that? Okay. This is kind of a roundabout way of doing things, right? Okay, watch. I'm going to change colors and I'm going to do this a different way. I'm going to cancel those, 1 on the top, 3 on the bottom. I'm going to write the top as radical 2, and I'm going to say, hey, isn't this radical 7 times radical 2? Isn't that the same as radical 14? Do I have factors that are the same on the top and the bottom? Yep. 1 over 3 radical 7. Did I get to the same place 2 different ways? Personal preference, whichever one makes sense to you, but I'm not done yet because somebody raise their hand and tell us why we're not done yet. Why are we not done yet, Brittany? Radicals in the denominator. If I'm going to simplify a radical, I need how many factors? 2. How many 7's do I have? How many more do I need?
1.
So I'm going to multiply by 1 more radical 7. So we're going to multiply by radical 7 here and radical 7 here. If you brought a 7th grader in here, their head would explode when you looked at this. You're going to take that and make it look more complicated by multiplying it by radical 7? Yeah, because we know what it does. So the top turns into radical 7. The bottom turns into a 3 times 7. Now, at this point, you ready? We doing okay? Somebody's probably thinking, hey, can't you cancel this 7 with that 7? What's the answer to that? No, because this is not a 7. It's not really a 7. Throw it in your calculator. It'll give you 2 point something ugly. So that's not really a 7, so you can't cancel something inside a radical with something outside a radical. So your answer on this one is radical 7 over 21. And just like I said a few minutes ago, if you want to type in the original problem and see if you get the same decimal as your answer, that's a good way to check and make sure that you got it right. Okay, everybody good? Okay. I'm going to go slow. I'm going to give you a mental head start. What do you think we're going to do? It's underneath the same radical, and I can't simplify 7 over 18. But I can think of this as 9 and 2, or that's 3 and 3. So I have radical 7 and a 3 outside and a 2 stuck underneath. So what do you do to finish that? It's a question for you. What do you do to finish it? How do you rationalize the denominator here? Do we care if the top's ugly? Nope. What we care about is the bottom. Okay. So those are kind of rhetorical questions till now, but now I need an answer. What do you do? I got 3 hands up. I'm hoping that means there's like 18 bashful people in here, but you really know what you're doing. Lizzie, what do we do?
Multiply by radical 2 over radical 2.
Very good. We multiply by radical 2 over radical 2, because what we're multiplying by a 1. Multiplying by 1 might look funny, but it doesn't change the answer. It just changes how we're going to write it. So we get a radical 14 on the top. Now we have that pair of 2's. We made it so we had enough pairs underneath the radical. This is a 3, that's a 2, so I get a 6 right here. Like I said before, if you type in radical 7/18 and radical 14 over 6, they should give you the same decimal equivalent. Everybody got it? Okay. How many problems are on the worksheet? Oh, there's not a backside? That's way too nice. That's way too nice. Do you think we need to get rid of any? Yeah, I'm not thinking so. I'm not thinking so. Let's do them all.
Multiples of 12.
You're going 8?
It would be if we don't get 3.
I can go with 8. I'm going to go with 8. Thank you, Si. Okay? Get rid of multiples of 8. Whoa. Do we need to work on that whole unison thing again? Hey, get rid of multiples of 8, guys.
Thank
you.
There we go. Thank you very much. Okay. You do have homework. I apologize. Just the way it is sometimes.
Right now.